recording is rolling. So Friday, hey, we're just a couple hours from the next weekend. You guys just turned in your chapter 4, chapter 5 homework. So thanks for doing that. So federal impact forms, that was last time. So that's through your 5th period. So you guys know to bring those in by the end of next week. Okay? You guys' kinematic quizzes, I just handed those back. And also the solutions I just uploaded this morning to Google Classroom. So if you want to do corrections and handwrite out those for partial credit back, then you guys got the solutions that you can refer to. And I have you guys' next quiz ready to go. You guys see clipped on the right side of your desk a page that looks like this on the right side of your desk. So it's got some free body diagrams set up on one side. On the other side, I see a baseball falling through the air. There's some air drag. You see that? All right, so that is you guys' next Open Notes take-home quiz, and that is due 1 week from now, the next Friday, which is going to be October 1st. Questions so far? You guys good with everything? All right, so before we get to the main thing today, I do want to go over a problem with you guys that involves a ball bouncing off a wall. Mostly because I was going to do this with my AP kids, and if I don't do it for you, then I'll be confused as to who got this information or not. So a ball bouncing off a wall, how much force? What's the average force of a ball bouncing off a wall? Something like that. Well, let's see, what information would you have to know to answer something like that? So let's get a wall. Here's a ball. There's a boing. I'll do a V throw. And it's going to rebound with the, say a different scale, probably be rebound. Here's the ball. You do need to know the mass of the ball to make this work. And the fourth thing you have to know 4 things: the throwing speed, the rebound speed, the mass of the ball, and also the time of contact with the ball. I'll call it delta T, like a time interval. So if you know those 4 things, you can answer what is the average force. Say F average of wall on ball. So the framework for this is going to be Newton's second law of motion. So maybe I'll start with that. Say F equals ma. That's been a real star formula the last couple of weeks. Newton's second law of motion. The question is, what is the force? So that's what we're solving for right there. The mass of the ball, that could be one of the given values. Because so far we're looking pretty good. Now, acceleration. Isn't that ball undergoing a huge acceleration at the point of the wall? It's changing its motion really dramatically, isn't it? So for that one, I'm going to go back and substitute the original definition of acceleration that I told you guys, which is a rate change of velocity. So the average force from the wall, that's what this is, average force from the wall, is equal to the mass of the ball times the rate change of its velocity, change of velocity per time interval to do that. Okay? And that is going to be mass of the ball times, I'll say V rebound minus V throw all over time interval. Like that. Okay. There you go. Now, I'll make up some numbers so you guys have something to refer to. Let's say the bounce of the ball is like 2 kilograms. Let's say you throw the ball at the wall at like 10 meters per second. And the ball rebounds at, hey, can the rebound speed be more than 10 meters per second? Is that physically possible? No. Unless maybe the wall is moving, maybe in that case. But the wall's just still like most walls are. It's got to be, that would be an upper limit. So it could go up to 10 meters. Maybe I'll do like 8 meters per second, maybe something like that. Okay. And the time of contact with the wall, isn't that going to be a very brief interval of time? Yeah. Okay. So maybe I'll make it like 50 milliseconds. So it'd be 50 divided by 1,000 seconds. Okay. So there's some example numbers in blue ink. Right. So all you have to do is just feed those example numbers into the setup. But there's one last trick before you can get this exactly right, okay, which is, I wonder if you guys can figure out exactly what is this delta V, the change in velocity of the ball. So say the ball was originally going at 10 meters per second, but it rebounds at 8 meters per second. Guys, what is the difference? You guys ready for sort of a trick question? I wonder how many of you guys are going to get this. What is the difference between 10 meters per second to the left and 8 meters per second to the right? And the answer is not 2 meters per second. What's the difference between 10 left and 8 right? And the answer is not 2. 18. 18. Yeah, you guys got it. Hey, if you don't quite see it yet, put this on my number line. So let's put, say 0 meters per second here. We'll go negative 10 meters per second there, and then positive 8 meters per second here. That's approximately the scale. If you didn't see it before, I bet you see it now. So the difference between positive 8 and negative 10 is actually 18 meters per second. That's your delta V. Deal with this, right? Okay, so then once you got that, now you can definitely keep the number 7. So we got 2 kilograms times a change in velocity of 18 meters per second, all divided by 50 milliseconds, so 50 over 1,000. Right? That would give you some force in newtons. Right? Guys get that? Let's get to what we're actually doing today, which is very known frame. Here we go. Okay, so I'm gonna flip my screen for you guys. Let's see, present screen to share. You guys are looking at one, a very known frame. I want to say it's the map of the Netherlands, I think it was, but got video, so scroll back and show you guys what you're looking at. You guys see it's sort of like a paper cutout of a factory there, and you guys, look at those pulleys. You guys have red pulleys; these are black, but you guys know what pulleys are. You guys have got your hands on those the last couple of days. Go back to the very beginning of this and explain what's going on. So you guys today are going to solve an economics problem using physics, which is actually the fastest way to solve this. So suppose you want to build a factory and you're trying to determine the optimal location of the factory. And what's going to constrain that or determine that is transportation costs. So in my example, I'm going to say that we're making pencils. Let's say we're making pencils. And you got different raw materials. So maybe a raw material might be like the wood from the forest. Maybe you need this little metal bit right here. So that could be, maybe there's some like metal mine somewhere. You could have other materials possibly. I'm just going to strip it down to 2 for example in class. And then there's going to be like some route. You need to route those to a factory. And then in the factory, you turn all those materials into, say, pencils, and then ship those out to, on this slide, it says market center. It could be like some town or something somewhere where people are buying pencils. Okay. Now, if the transportation costs of all these materials is equal, if it's just the same everywhere, then you probably want that factory pretty centrally located to minimize distances and therefore minimize transportation costs. But maybe it's the case that some of these materials are more expensive to transport than others, right? Like maybe the finished product, for example, would be everything put together, so maybe it weighs more, something like that, right? Now, whatever the highest, say, per unit cost of transportation would, like per distance moved, like cost per kilometer to move these materials, if something's very expensive to transport, do you want your factory to be very close to that point or very far away from that point? Very close, right? So, for example, if maybe one of your sources is wood from a forest, and maybe just the timber just is like bulky and difficult to work with, so that's really expensive. Yeah. So you're right. You would put the factory really, really close to that, so that it doesn't have to go very far, and that would minimize the production costs from a transportation point of view. Oh, here is Very Non himself. Now, what you could do to solve this problem, well, one way to solve it is with lots and lots of trigonometry and economics, but the fast way to solve it is actually with physics, with a Very Non frame. And what you can do is replace each of these sources with one of those pulleys, one of those red pulleys from your lab station, and see all those dashed yellow lines, replace those with string, and tie all the strings together. And what'll happen is that the natural equilibrium point of the factory to minimize transportation costs will naturally emerge. Here's this sort of from the side. Yeah, so see each of those pulleys could represent some source of materials or the place where you're trying to sell the pencils eventually. There's a string wound around, and see those weights that are hanging down vertically? Those are going to be proportional to the transportation costs. So if there's one transportation cost that's like twice as much as everything else, you can represent that physically with the weight that's like twice the weight, like that. And then all these strings are tied together in the middle, and that's where they put this factory. So the location of the factory will naturally emerge. Okay. There's the pulley from the side. There's some pulleys. lab weight. All right, let's see this thing in motion. You guys ready to see this in motion? Here we go. Ooh, look at that. See there, let's do instant replay. So there was one equilibrium point. There's the factor right there, and the weights, yada, yada. Right? And then this guy's going to put on some more weight to one place. That's to say that would increase that particular transportation cost. You guys told me that you should move the factory closer to that point because it would be more expensive to transport. And you see that factory? Yep, definitely moves close to that point. So there's a new equilibrium point like that. Okay. So let me switch back to projection. So show you guys what's going on with this lab page. Now, sort of running low on printing budget, so we're just going to do one paper per team. You guys put several names on papers, okay? Also, we're short on time today, so we got here 3-5. Okay. So you guys won't have time to finish this today, but at least get a good start, and probably we'll finish this on Monday. But show you what's going on. So I've got 3 scenarios. So I've got an example scenario that I wrote in all the numbers for. I've got scenario A and scenario B. See how they all kind of same-ish, same format. So what numbers are we looking at? So I give you 3 transportation costs, and in the in my example number, I just made them all the same, but that could change. Okay? And then 4 locations. So if you're trying to make pencils, then well, you need some wood for this wood body. So get that from this forest. You're going to need this middle bit right here. So that might come from, well, I said copper mine. That might be representing that. And, well, I guess that's all we need to make the pencil. Let's, well, I guess there was an oversight on the graphite. But we're going to take these pencils that can't write very well and send them to this town. And notice I gave you guys coordinates on all of these. So the coordinate of the forest is, hey, it's an XY coordinate. That's a Cartesian coordinate. 0, 0, right? And then 0, 122, 122, 61. Right? And then some factory location will naturally emerge from that. No, we're only getting these numbers like 122. Like, why did I pick that number for my example? Well, I will tell you guys why. Because that takes advantage of your guys's lab table dimensions. So lab table. Turns out that your lab table is exactly 122 centimeters wide. Right, so how does this page line up with that physical lab table? Let's do it side by side. You guys see those. So I told you guys the forest is at the point 0, 0. So let's put the forest right here. And I'm going to represent that with one of these, this pulley. So we put a pulley right there, right on the corner of the table. That's at the 0, 0 mark. And that is the forest where all the wood's coming from. Next location, the copper mine. That's seated at the coordinate 0, 122, which is this distance this way, which is about right here. So put another pulley right there, and I'm going to call this copper, or copper mine. Okay. Suppose that's the only 2 inputs you need, and got to put a factory somewhere. But then we need to take this these finished goods to this town. This town's sitting at 122 over 61 up. So 122 over 61 up. That is right here. Here's the town sitting at, oh, whoops, I forgot to label the coordinate. 0, 122, and 122, comma, 61. Okay, so go like that. All right, now, okay, so I just made it some locations. And then if you tie 3 strings together, and, and also tie lab weights on the other side. Now, remember, the transportation costs are represented by these lab weights. And if they're all the same, then you can just do like 100 gram lab weight, 100 gram, something like that. Later on, you can change those if you need to, right? Like the next example, but in a minute. Right? So I've got a lab weight hanging over here, say 100 grams. Got lab weight right here, 100 grams. I got lab weight right here, 100 grams. Okay. String, string, string. Okay. And then all these strings, I can tell you exactly where the equilibrium point will be because I calculated it. You guys can check this too if you want to run these numbers and see like, how close is this? Okay. It ends up being right at the point, and this would be your factory. That's where you want to put the factory to minimize your transportation costs. At the point, I wrote right here, 35 centimeters over, 35.2, really precise, and 61 centimeters up. Okay. That is exactly where you want to put that factory. Right, so the goal was, again, you guys are going to run out of time today, but we might finish this on Monday, I'm thinking. So hold on to this paper. You guys can do this as a group. Scenario A, I gave you guys some weighted costs, which again could represent lab weights. If you really can't dig out lab weights with this ratio, you can cross these out, make up your own numbers. But I was trying to guide you guys along a little bit. You can put the forest, the mine, and the town wherever you want. Could be the same locations as before if you want. And then figure out where does the factory go? What's the XY coordinates of this factory that emerges from that? Okay. And then scenario B is completely open, so you can make up all your own numbers. Okay. Any questions about? All right, so you guys got the rest of the class to work on this. When the bell rings, just hold on to this paper for now, and we'll figure out what we're doing this for finishes on Monday. I'm going to leave this up here for you guys, and I'll walk around and help you guys out.